done. So the format of the exam, you're going to see in terms of the types of problems that I ask you, kind of a mixture of everything. Of course, as I was talking about before our break, you all are going to send me exam questions from your presentation, so those will be on there. And I expect most of those to be true, false, multiple choice, maybe fill in the blank style if some of you are feeling a little adventurous, right? I will also probably ask you some questions that are true, false, multiple choice, fill in the blank style questions, along with at least probably a few that are longer answer questions. Especially for a graduate level class, I almost always like to ask at least one or two questions that are longer form answers about, especially about a specific topic that we've covered in class. I think that's a reasonable thing to do for graduate students. There might be some very basic arithmetic involved, as in stuff you can do with pencil and paper, but honestly, it is open notes, and I will allow you to use your computers for that too. So if you need to whip out a little calculator or use some arithmetic, it's not a math class, right? So I'm not judging you on your ability to crunch numbers, but there might be some mild number crunching involved on some of the problems. That's really about it. I don't expect the exam to take the full 90 minutes for you all. I've been watching you take notes, so I think that the amount of note-taking I've seen gives me lots of optimism that the exam's going to go pretty smoothly for everyone. You could honestly even, so like watching the videos in the middle of the exam with the audio on, that's probably no good. But there's like transcripts and stuff, right, of the videos that are on YouTube, so you could easily take a look at some of the transcripts and go through some of that stuff that way if you really wanted to. Plus all the slides are available to you, so trying to make it as low stress as possible, although it's an exam, so there's inevitably some stress, just like with the presentations. I think some of you are probably more scared of the presentations than the exam, but yeah, that's okay. It's kind of my job to make you guys squirm a little bit. I think that's how we learn, right? That's how we grow, is by doing things we're a little uncomfortable with, and then we get a little bit more comfortable with them. That's how learning happens. Question? So actually, I think a lot of the stuff that I'm going to be talking about today is going to be a good example of some of the arithmetic stuff that I might ask you. I'm not sure that we've covered too many topics that have been super math heavy before now, right? I know I've showed some formulas, so maybe speed up would be a good example, right? If a program takes X amount of seconds in a serial, and this proportion of the program is parallel, how much speed up would you expect to get? I think that's a reasonable example of a math question that you might expect to see. Some of the stuff we talked about, though, is not math at all. Like programming paradigms and stuff, there's not going to be math related to that kind of stuff. It's more just content knowledge. Yeah, great question, though. There won't be a ton of math. As I said, it might show up a couple times, and I will keep the numbers very easy. So if you crunch the numbers and it's got like 10 point places after the decimals, you almost immediately know you took the wrong turn. So I'm going to make sure the numbers are nice and easy and even if you know what you're doing, which I'm kind of assuming you all do because you all show up and pay great attention. So it's been a great class, at least from my experience so far. And so yeah, thank you all for that. Any other questions? I'm happy to answer more questions about the exam or presentations or anything else y'all are anxious about. Anything I can do to help relieve some of that anxiety, very happy to do. I know Austin and Drew are probably feeling the most comfortable in this room right now because they're done with their presentations. But I'm really excited to see the rest of the presentations. Those two honestly energized me a lot. I thought it was great to see them all. But let's talk about networking and topologies. This is going to be a very important part of any high-performance computing system because we're talking about systems that are very large, and there's just no way once we're scaling up that big, there's got to be a way for them to be connected, communicating to one another. So this becomes a huge, huge part of any large high-performance system. And so let's take a look at some common examples that maybe you would expect to see on a smaller scale, and talk about why those don't necessarily work at a much larger scale. So one very common example, if I have, even probably on your, well, maybe not on your laptop, but maybe on like a nice higher-end laptop, if you got a lot of cores on it, you can buy, 16 cores, I think, is pretty common these days for higher-end laptops. But those cores are going to have to talk to each other somehow. So having some kind of a shared bus, which is not the same as shared memory, right? Shared memory is a programming paradigm we talked about where they can communicate by writing to two different locations of memory. But sometimes they can send messages directly using a bus. And typically, all of the processors or all of the cores are going to be sharing that bus, right? Hopefully, pretty easy to see that if I scale that up to more than a couple dozen or so processors, that bus is just going to get overloaded, right? If I put 1,000 processors all sharing one bus, and they all try to send messages to each other at the same time, that bus is going to get filled up, and a lot of those messages are going to get stuck. So using a shared bus is great on a small scale. Lots of our personal machines, I'm sure, have some kind of similar system. Another way we can think about this to try and solve the shared bus problem is okay to say, hey, instead of having one major highway that everybody uses, what if we have lots of small links and we just connect all of the cores to each other directly, fully interconnected? Again, if you're dealing with a small number of cores, that's actually not a problem. And from a communication perspective, it's like the ideal, right? It's like the best possible scenario. But from a practical perspective, it doesn't work out very well because as we start to increase the number of cores to a much larger scale, every time I add even just one new node to my system, I then have to add one new wire to every other existing node to my system. So if I'm going from 8 nodes to 16, maybe not so bad, but if I'm going from 512 nodes to 1024, that just became a much bigger problem in terms of where do all those wires go? I got to pay for all those, like the cost. It's going to scale much faster and become very quickly cost prohibitive. So we need to figure out an in-between route, and there's actually a whole bunch of different in-between routes that we can talk about, and that's sort of the goal for the first part of today. First, though, we need to talk about some graph theory. I'm assuming that most of you have probably, thought of or talked about these kinds of graph theory concepts, but it may have been a little bit of time since you've taken your data structures and algorithms class during undergrad. Usually first and second years are taking that. So just as a little bit of a refresher, if we're talking about our network as a graph, I think the first questions are pretty straightforward. The nodes are going to be, well, that word node, I guess, kind of go both ways, right? The nodes of our graph could be the nodes of our machine as well, or the processors, the cores. I kind of use those terms interchangeably, although it is possible for one processor to have multiple cores on it, of course. But then the edges are going to be the actual physical links. Are those edges in a network going to be directed, undirected? Any opinions? Think about what it would mean if they were directed. That would mean a processor could send a message. Processor A could send a message to B, but for processor B to send a message back to A, there would have to be a second link, a second edge. That's typically not how it works. If I have two things networked together, that's a two-way street. It's not a one-way street. So undirected edges on our graphs, at least for the graphs we're talking about today. And then these are some terms that we're going to be talking about. Actually, maybe not the first one so much, but the degree is the number of nodes in our graph that a single node is connected to. Typically, for a high-performance system, we're assuming that all of the nodes in our system are going to have roughly the same degree, if not exactly the same degree. So if I have 100 nodes in my system, and each one of those is connected to 5 other nodes, then I would expect all of them to probably be connected to roughly 5, maybe give or take a little bit up or down, depending on the exact topology, as we'll see in a little bit. But we're not going to have vastly different degrees in most standard topologies. The diameter is actually a really important one to think about when it comes to high-performance systems. The diameter is asking us what is the maximum shortest path between two nodes. So what I mean by that is if we're going to have, we want to know what is the longest path, essentially, between two nodes in the system. And that tells us if we send a message, right, we're guaranteed that a message is going to get from point A to point B in at least that much time, as it takes to traverse the longest path, or less. So it's providing us the upper bound on how long it could take to send a message in this system. Not all messages are going to take that long, right? Only the two nodes that are the farthest, and I use that in quotes because farthest is not done by physical distance, but by actual links, actual hops that it has to make through the network. But based on that information, we know that a message is going to take, at most, the diameter's amount of time to send that message. And in most cases, even a lot less than that if the nodes are closer together. So those are some important things to keep in mind as we start to talk about some actual topologies. Congestion is another one important to think about. We'll actually try to characterize congestion a little bit later on today, but for now, just to define what we mean by congestion, we're really asking, okay, is it possible that more than one processor is going to want to use the same link at the same time? And the obvious answer is almost always yes, right? The only way that we would actually avoid that situation is by using a fully connected topology where every single node is connected to every single other node, has its own dedicated link to every single other node. In any other situation, it's almost guaranteed that congestion is going to happen at some point because there are fewer connections than there are nodes, and so everybody decides to send a message at once, which is not necessarily the most common event, but can happen, right? Eventually, there's going to be some that are congested, and so then the question becomes, well, how does that affect, the execution of the machine? In this example, we see that all of these nodes on the bottom are sending one message to the nodes on the top. And so for the two on the outside, they get nice free access. They get a link all themselves. But the nodes that are closer to the middle, they have to share. And so now these processes at the top have to have extra latency, extra time to receive those messages through no fault of their own, right? So that affects all kinds of things like load balancing, because these nodes then theoretically would finish faster than the ones in the middle, since they're going to theoretically receive their message first. And we don't even necessarily know, in a lot of cases, which one of these is going to get to use that channel first, right? Maybe the first one who gets there makes it. Maybe the router chooses to do something different. There's all kinds of things that can come into play there. All right. So if we want to try and characterize how congestion is going to affect our machine, a lot of time we're talking about the bisection width. So the definition of bisection width is how. Here, I got this in my notes. I want to make sure I say this properly. It's the minimum number of links that have to be cut in our network to make two unconnected graphs of equal size. So I can't just find one isolated node and chop it off and say that I bisected the graph. I'm trying to bisect it equally, so there's two equal halves. So what we're really saying is, where's the bottleneck, right? Where is the point where if all of them send messages at the same time, what's going to get the most congested? Those are going to be the links that we're often cutting to split our graph into two. And that's what's known as the bisection width. Now, that's sort of an idealistic view of our networks. The bisection width is kind of making an assumption, which is not true, that only one message can go through a link at a time. Actually, the last slide kind of made that assumption as well. In practice, that's not true. The bandwidth of our links affects how many messages can be sent down that link at a given point in time. So bisection bandwidth is this idea of bisection width, but also with the bandwidth taken into account. What is the maximum bandwidth of messages that I can send down these particular links before they become saturated, and effectively cuts the network into two, because those links are now non-functional because they can't carry any more traffic. Redundancy is also a function of the bisection width. So you can think of redundancy as if I were to cut just not a bunch of lines, but if I were to just cut a single line, what are the chances that my message could still make it to where it's going? So the larger the bisection width, the more redundancy I'm going to have, right? Because if I have to cut 5 lines to fully separate my graph into 2 halves, that means that, well, theoretically, I could cut 4 of them, and it would certainly hamper the performance, but it would still work, right? It would still be able to get messages from point A to point B in the entire graph. The graph would still be connected, so still functional in that regard. So what we're going to do now is take a look at some basic topologies and work our way to some of the more complicated ones. We're going to take a little detour after that, and then come back to an actual case study. And hopefully I have time to get through it. We'll see. Take a look at an actual case study from an actual supercomputer. Talk about the specific topology that they use. So first, let's talk about a linear array. You get to see my wonderful MS Paint drawing skills. Normally I would do this on a whiteboard or something, but I can't record that, so I've had to start doing them, drawing them on my computer. But a linear topology is probably the easiest one to understand, right? If I have a whole bunch of nodes here, and I know these aren't drawn equally, but just pretend that they are in fact the same because it doesn't really matter. So this is a linear array, right? And of course, we're talking about this at scale. So in this particular example, I just have 4 of them connected together. But in a real world example, we'd be talking about thousands of these all connected together in a big single line. I hope that this is very clearly not the best approach. What's the bisection width of this guy? It's just 1, right? Pick one. It doesn't even matter which one. Just pick one. Actually, it does matter which one because it needs to be equal. I take that back. So we would actually have to chop this guy right here in the middle to bisect it into 2 equal halves. Not a lot of redundancy there, right? That one link goes down, and we're in big trouble. Also, I mean, with a linear array, the diameter, what's the diameter of our linear array? If I have n nodes, the diameter is going to be n, right? Because there's going to be that many hops between the one on the very far left and the one on the very far right. So this is another great example of if I have a small setup, maybe not too bad. It's certainly simple, right? Certainly very simple. Doesn't require a lot of connections, cost effective if I'm worried about costs. But in terms of practicality, not so great. So a step up from that would be to turn it into, I know it's not going to look exactly like the description, but where's my, come on now. Why can't I draw? Or am I just not doing it right? Oh, there we go. If we just add one more link to this, it's no longer a linear array, it's now a ring. It's now a ring topology. I know it doesn't look very ring-like. I didn't want to have to rearrange all the nodes to make it look like a ring, but still technically a ring. And so we get a little bit of extra redundancy here. The bisection width of this is now 2, right? I have to chop it. I have to chop the same one as before, but then also this new one that I drew to get them fully separated. So it does provide me a little bit more redundancy. If one of these links goes down, well, I can just take the long way around, right, and still get to where I'm going. That's a good thing. The diameter of this is now also 2, right, because I've effectively cut the distance in half of where I need to go. If you use these outer extremes as our example like last time, right, I can get to that much more quickly using this direct link. So now the longest path is between this guy and this guy, or this guy and this guy, or this guy and, well, yeah, I think I already said that one, but yeah. So now the longest possible link between 2 nodes is half the size. And if you extend that out to n nodes, it's actually still a bisection width of 2 for any ring, regardless of the number of nodes. The diameter would be n over 2. So however many nodes you have cut in half, right? Those are simple examples, though. So let's take a look at some more complex examples that are fortunately already drawn out for us, so that I don't have to draw them, because they do get more complex. Let's talk about 2D and 3D arrays. So a much more natural setup, especially if the data or the problem that you're solving, fits in a two-dimensional or a three-dimensional kind of format. So many physics simulations, of course, would love to be set up in a two-dimensional or three-dimensional format because we live in a three-dimensional space. So it makes a lot of sense to do it that way. There's actually not a three-dimensional example up here. These are both two-dimensional examples, right? This is a straight grid, and then this one would be a torus, a two-dimensional torus, where the torus effect is from kind of like with the ring, where we loop it back around to the other side. Not just horizontally, but vertically as well, right? So we see the rings going from top to bottom. There's kind of a reoccurring theme here, though. What's the bisection width of that first guy on the left? It's a little tricky. It's a little tricky in part because there's not an even number of nodes. There's 15 nodes, so you can't split it exactly in half. So the bisection width, obviously, I want to do it exactly in half if I can, but if I can't, you just got to get as close as you can. So how many links would I have to cut to get 8 on one side and 7 on the other? There's a couple different ways you can do it. Yeah, I think 4 is right. I'd have to cut 1, 2, 3, 4, for example, would get me there. I think there's other ones that you could choose to cut. If we let's try to standardize this a little bit. This is not a very good sized grid because in practice we would almost always choose an n by n grid, make it uniform. This one's not uniform. Although I guess costs and other things could affect that decision, right? But in an ideal case, we would do an n by n grid. So let's assume 4 by 4, 5 by 5. What would the bisection width be in that case? For an n by n grid, bisection width would be it would just be n, because you could just chop it right down the middle. So this is imagine if we had 2 more rows down here to make it 5 by 5. I would just have to chop 1, 2, 3, 4, 5. If it's 6 by 6, we just have to go right down the middle, right, to do 6 by 6. So it's always going to be n for an n by n grid. What's the diameter of this guy on the left? We're still looking at the left one. Making you guys do some work today. I think it's from these 2 corners, right? Those are going to be the farthest apart, either those 2 or these 2. So 1, 2, 3, 4, 5, 6 is going to be the diameter. But again, we're computer scientists. We like to talk in generalizations. So for an n by n grid, where we have the same number of rows and columns, what's the diameter going to be? 2 times n. Actually, 2 times n minus 1, I believe, right? If we imagine our 5 by 5, then I would...
n minus 1 times 2.
n minus 1 times 2, I think that's it. Yeah, n minus 1 times 2. So if it were 5 by 5, for example, to go from this corner will be 1, 2, 3, 4, 5, 6, 7, 8. So that's 5 minus 1 to get 4 times 2. Yeah, n minus 1 times 2. That's what I have in my notes, which I know is cheating, but no, it's not. It's just being prepared. Just being prepared. All right. Let's step it up a notch and talk about this guy on the right. What is our bisection width for this torus? Makes it a little harder to think about. Worry about those wraparound connections too. We still want to split it into 7 and 8 just like we did before. So, I might start by trying the same connections, cutting those 4, but then I have the wraparound connections I have to worry about as well. So this one for sure has to go. And then all 3 of these have to go too, right? To get those out. So 1, 2, 3, 4, 5, 6, 7, 8. Diagram. And what's the diameter of this guy? Which 2 are the farthest away? Because it's not the corners anymore, right? The corners we can actually do pretty fast. 1, 2. Is there any farther apart than that? to a corner, right? The middle to a corner would be 1, 2, 3. I think that's going to be the farthest, yeah, in this particular example. And of course, like with the other ones, I probably want to ask you to generalize it. It's tricky. I may stop asking you to figure out what these are and start telling you what they are, because the more difficult topologies are harder to reason about. For an n by n torus, so not just limiting ourselves to this specific example, but if I'm talking about any square torus, the bisection width is always going to be 2 times n, because you have to cut, not just go straight up the middle like you would for a non-torus, but you also have to cut n of these wraparound sections as well to fully bisect. And then the diameter the math gets a little bit even more complicated still. The diameter of an n by n torus is 2 times the floor of n over 2. And you have to take the floor because it differs depending on whether n is even or odd. So I'm not going to, we could spend all day talking about how to compute all those things. I think it's more important just to recognize what these actual values are. And that's not even to talk about a 3-dimensional grid, which is perhaps even more common in some applications than 2-dimensional grids and toruses. For a 3-dimensional n by n grid without the torus, we're looking at a bisection width of n squared and a diameter of 3 times n minus 1. So adding that third dimension just kind of bumps up the numbers. And you can do toruses with 3-dimensional as well, but I'm not even going to go there for this particular. I think we've hammered this example enough, so we're going to move on. Actually, I think we already answered these ones. Yep, we just answered those. All right. Let's talk about hypercubes. So this is another step towards, we're adding more and more complexity, but again, our goal is to kind of try and maximize that bisection width and that minimize that diameter to keep our, so what else can we do to try and up the bisection width and reduce the diameter of our topologies to ensure fast message passing? So we're working our way up here. Obviously, 1 dimension is a line, 2 dimensions is a square, 3 dimension is a cube, 4 dimensions. So wait a second, we don't have 4 dimensions, but in this particular context, the 4th dimension, which we call a hypercube, is 2 3-dimensional cubes where we have connections. So all 4 of these top points are connected to their corresponding nodes on the other side, and same for the bottom plus. That's what's known as a hypercube. For an n by n hypercube, we're really just, so this would be an example of a 4-dimensional hypercube where we have 4. So if we stepped it up to 5 dimensions, we actually just keep this same setup. It's just the cubes grow bigger on either side. So a 5-dimensional hypercube would have a 3 by 3 cube on both sides, and 6-dimensional would have 4 by 4 on both sides, et cetera, which is not how we typically think of dimensions in the traditional sense, but when we're talking about hypercubes, that's what we mean by dimensions in this particular case. And for those, I mean, even for this particular example, we could maybe try to reason about what the bisection width would be. For this simple example, I think it's pretty straightforward. We just hack all of these, right? Just hack through all of those. So that would be 8 connections in this particular case. But if we try to generalize it to an n by n case, we get a bisection width of 2 to the n minus 1. So in this case, it's a 4-dimensional hypercube. So we subtract 1 from that to get us 3, and 2 to the 3rd is 8, which is how many we have to slice here. If we bump it up to a 5-dimension hypercube, it would be 2 to the 4th connections that we have to cut. So you can see that the bisection width grows pretty rapidly with the dimensions that we had, with the cost of, I mean, this is a much more complex topology setup than a simple 2-dimensional grid, or even a 3-dimensional grid, a 3-dimensional cube would have for us. And And as far as the diameter goes, let's just start with this simple example that we can see up here on the screen. Which of these two nodes are the farthest apart? I think we're looking at the corners still, right? So if I take like this corner down here and this corner up here, that's going to take me 1, 2, 3, 4 hops to get from one corner to the next. I can't see a faster way to do it. And that's coincidentally the number of dimensions that we say this hypercube has. And fortunately for us, the equation for, in general case is that simple. If I have a 5-dimensional hypercube, then the diameter is going to be 5. And if I have a 6-dimensional hypercube, the diameter is going to be 6. And so on and so forth. And this one is actually pretty common. Hypercubes are not a terribly uncommon setup to see in supercomputing setups. In fact, we'll see maybe a little bit of a spoiler, although I'm a little worried I won't have time to get to it. Later on today, we're going to see an example of a 6-dimensional hypercube. It's actually been implemented on one of the fastest computers in the world. Yeah. One other thing that's worth considering is, okay, this topology is much more complicated. We still have to write code that can operate on this, right? And so the nice thing about doing it this way, and we'll see this a little bit later as well, it's possible to actually treat this as a 2-dimensional grid or a 3-dimensional grid. If all we really have to do is just pretend like some of these links don't actually exist and kind of flatten it out a little bit, if you will. Maybe flatten isn't the right word, but you kind of get where I'm going. Let me do you one better and show you. I think I have an example. We already answered this question, so let's focus on this one. Projecting a grid down at the bottom here. So this is on the left what we might use for traditional. These aren't even hypercubes, although you can imagine this as 1/2 of a hypercube, since we just need 2 of them. But you can imagine this as a simple way of numbering your hypercube. And the nice way of numbering it this way is that you'll notice that each neighbor differs by only a single bit. So this node 0, 0, 0 only differs by the 1's bit. This node 0, 0, 0 only 0, 1, 0 only differs by the 2's bit. And this one only differs by the 3rd bit. So as far as addressing goes, that actually is very convenient. I can address using ands and ors, and maybe some exclusive ors and whatnot. But if I'm trying to do things in a grid-like fashion, it makes things complicated because 0 to 1, and then 1 is not next to 2. 1 has no direct link to node 2. So if I wanted to treat this even as just a linear array, right, not even a 2-dimensional grid, using this numbering scheme is difficult. But let's renumber them, right? We get to decide which node is which address, which node is which process number, or whatever the case may be. So with some clever renumbering, and the textbook goes into a lot more detail on how to do this renumbering than I'm going to go into, but with some clever renumbering, we actually can number it in such a way that I can touch every single node in sequential order. So 0 to 1 to 2 to 3 to 4 to 5 wait a second, did I skip one? 0, 1, 2, 3, 4, 5, 6. 7, and then at this point we would take one of our links over to the other hypercube and then just follow the same pattern once we got there. So that's for a 1-dimensional array. You can also apply the same renumbering scheme to try and get you a 2-dimensional grid as well. But again, I'm not going to go too far into the weeds on that particular point. Just trying to show that from the programming perspective, right? Let's say that we have our topology set up in a hypercube way. That's great. So it allows us to use it in the general purpose way as a hypercube. But if I also want to use it in a grid, I can do it that way. And a lot of this can be done without the programmer even having to know about it. So we can have a layer in between our user code and the actual message passing that happens on the wire that kind of does this renumbering based on our application, so that I, as the programmer, don't have to even take that into account. When programming, I can code it up as if we're just a regular two-dimensional grid, which most programmers are already very familiar with and can work with much more easily than trying to keep that mental map of a hypercube in your head while you're writing your code, which kind of sounds like a nightmare. So a lot of tools have been written to help make that process easier. All of these, actually, I should have mentioned this up front, by the way. All of these slides and everything that I'm talking about right now are taken directly from the textbook. So you might want to jot that down in your notes. The textbook that's linked on the Canvas page. This is all from chapter 2.7. I'm not covering every single thing in that chapter. I'm just kind of giving the high points. But if you want to do some extra reading on this stuff later, or just kind of refresh your memory a little bit, that's where all these images are taken from. All right. Let's talk about something a little bit different now. All of the past connections kind of implied that there was some kind of link between nodes. When you say link between nodes, of course, a lot of people think about Ethernet, because that's kind of the de facto standard for networking in general. We're actually going to talk very briefly about InfiniBand, which I know I've mentioned a little bit before, but is much more prevalent in high-performance computing contexts. But what I want to talk to you about right now is actually something that doesn't require either of those things. Well, it still does, but on a smaller scale, because we're going to start to inject switches into the mix. And so less direct point-to-point connections, as Austin was kind of alluding to when he was talking about MPI. But let's put some switches into the mix. It does add some cost, but hopefully at the advantage of some efficiency and maybe reducing the complexity a bit as well. So the simplest switch network would be a crossbar, and you can kind of see where it gets that name from. In this case, we have 6 nodes. So if I want node 3 to be able to talk to node 0, that's what this dot represents. That means that there is a direct link between node 3 and node 0. So we actually can configure these crossbars on an application-by-application basis to say which nodes we want to be able to talk to which other nodes. That does take time, right? That does actually, it's not free. But all connections are possible under this setup. We have the same disadvantage, though, that we had if we were trying to do a fully connected network on the very first slide that I talked to you about. As I add nodes, this is going to grow in an n-squared fashion. So at some point in time, you're not going to find a switch that has 1,024 connections. They don't make switches that big, right? I think the biggest I've seen is maybe 96 or so. They might have a few that go a little bit larger than that. But they're also going to be expensive if you want to buy them that big. So cost becomes another prohibitive factor. But using this on a small scale, and then connecting a bunch of these small scale crossbars together, well, now we're talking, right? Now we're talking about something that might be a little bit more practical and a bit more useful. So enter the butterfly network. In this particular case, we're actually kind of connecting these, not really in a tree-like way, so there's no root, right? You don't see a root. But there are layers. And the more nodes we have, represented by the processor P labels here, the more layers we're going to have. So for 2 nodes, you can see that 1 layer is sufficient, and then 4 nodes is going to require 2 layers, 8 nodes are going to require 3, and there's a pattern there, right? We're looking at log n based layers based on the number of nodes that we have, where each of these is a switch, right? But notice that these are pretty small switches. They're just going 2 places. So we're not talking about big beefy switches. We're talking about very small, hopefully easy to acquire and maintain switches. This is actually another pretty common way of doing it, and it also has the added advantage of providing us with a uniform memory access. So butterfly networks, butterfly exchanges. If I want to send a message from here to here, it's going to take exactly as many hops as from here to here through this switch network, just based on the way that it's arranged. Part of the way it accomplishes that, you can see that down at the bottom, there's a lot more of these crisscrosses over the middle. So it does look kind of tree-like in that there's more concentration down here at the bottom than there is in the intermediate nodes. Kind kind of where the butterfly gets its name. But let's take a look. We can actually illustrate this a little bit more clearly if we take a look at an actual example of routing. Butterfly networks make routing a lot easier as well. So in this slide, I know it looks a little bit confusing. We have 8 nodes at the top and 8 nodes at the bottom, but these are actually the same nodes. They're just duplicated. So there's only 8 nodes total. There's not 16 nodes on this slide. Just want to make that clear. It's just demonstrated this way to make it easier to understand how the routing works. So if I'm trying to send a message from node 110 up at the top, node 6, down to node 3 here at the bottom, over on the left we can see that I'm just going to examine one bit at each layer, and that bit is going to tell me where to go to the next layer. So in this particular example, if I have a 1, if I have a 0 in my destination bit, I'm going to go to the right. And if I have a 1 in my destination bit, I'm going to take the path on the left. So here, I reach my first one. It says, all right, look at the first bit of your destination. That's a 0. Then I'm going to take this right path. All right, on this layer, I'm going to look at the middle bit, which is a 1, so take the left path. And then finally here, I'm going to look at the last bit, which is a 1. I'm going to take the left path. So we can generate the path just based on the destination address. It makes routing very, very simple, very, very straightforward. It's a nice advantage of these butterfly networks. What's the bisection width in the... Oh, man, you thought I was done asking you that question, didn't you? Nope. What's the bisection width and the diameter of such a network? Of this guy. Bisection width. Which wires am I cutting to split this in half? Anybody see it? I don't think it, yeah.
Is it 4? You got the old long ones?
Yeah, these ones right here. And that's going to be true for any butterfly network. Just look for the crisscrosses in the middle here. Even if you expand this out, so you'll notice that I'm always going to be using power of 2 nodes here, right? If I have a weird number of nodes, then, and that's true for not just this topology, but some of the other topologies we've talked about as well. I'm using powers of 2 numbers of nodes here. So from 8, I'm going to go up to 16, but even with that 4th layer added on, there's still going to be this crisscross. It's just going to be not 4 crisscrossing. It'll be, how would we generalize that? That's sort of the next question. Bisection width. Here I have 8 nodes and I cut 4 wires. So n over 2 seems like a good bet, and that would be correct. If I have 16 nodes, there's going to be 8 wires crisscrossing in the middle of my butterfly network on that final layer. So it's going to be n over 2 for the bisection width. That's really good, right? Compare that to some of the bisection widths that we talked about before. That's still very good. The diameter. What's the longest path? If you've been paying attention, this should be a very easy one. Even just think about the example we just did of this routing. So, number of layers. Yes, actually, you're absolutely correct. I'm guaranteed to hit every number of layers. So in this case, it would be 3. I did three jumps. This is an example of the diameter, right? Not only that, but I mentioned a slide back. This is a uniform memory access system. So regardless of what my source is and what my destination is, it's always going to take the same number of hops for every single one. So regardless of where I start and where I want to go, always 3 in this case, which is going to be log of n, right? There's 8 nodes, so log of that would be 3. And that holds up. If I expand that out, it's going to be log 8 of n hops, which is one of the, both the advantages and the disadvantages of this butterfly exchange topology. This exercise here says trace the path from node 100 to 101. Well, if I'm looking at 100 and 101, they are right next to each other. So it might be very tempting to just be like, oh, I just have to go boop, boop, and I'm there. But that's not how the routing algorithm is implemented, right? We are going to do it deterministically, consistently for every single message that gets passed. So if I want to go from 100 to 101, I have to follow the same mechanism. 1 says go to the left, and then 0 says go to the right, and then 0 says go to the right again. And here I am at 100. So even though they look like they're right next to each other physically, and they very well may be, I'm still going to travel through every single layer of the butterfly exchange every single time. It's uniform memory access, so that means that all of these processors are going to take the same number of hops, regardless of where we start and where we end. That's not true of any of the other topologies that we've talked about today, right? If they are physically close together, then I get there faster. And if they're physically farther away, or the links are set up in a different way, then it's going to take me more hops to get there. But in this case, it's not just the diameter that's 3, it's every single message that gets sent, 3 hops. So that has some advantages though, right? That makes it very easy for me to analyze traffic. I don't have to wonder, is this going to take extra hops or fewer hops? I already know off the bat exactly how many hops it's going to take for every single one. So as far as simulation goes, things like that makes it much easier to analyze the flow of network traffic. At the downside of, possibly missing out on some what seems like obvious efficiency if I've got 2 of them sitting here right side by side. All right. And then I think this is the last topology we're going to be talking about. Fat trees. So using a tree structure as a network is kind of a nice idea. The problem, so this is an example of a fat tree. And you can kind of see maybe why it gets that name, because these are our processors down here at the bottom in the leaf nodes. And these are our switches. So those are going to be what's routing packets. Now, if you imagine this is not a fat tree, obviously in a traditional tree, we wouldn't have duplicates of these links here, or even quadruple of these links. But a fat tree says exactly that. The higher up I go in the tree from the leaf, I'm going to double this and then double that. And if there was another layer on top of that, then I would see 8 links between those nodes, right? That's exactly what it says to do. And why does it say to do that? Well, imagine if we didn't do that, right? Let's imagine these are all singly linked, like in a traditional tree. That root becomes a very obvious bottleneck in that case. Because any messages that are going from this side to this side have to go through the root. So that root is going to be the most popular, most trafficked switch in the whole system. So the idea is, well, okay, if I know that the messages are going to, these are going to require more traffic, or have to deal with more traffic on the way up, then I'll just make these duplicate links so that the pipe is wider, right? And they can handle more messages, they can handle more flow. And so that makes a lot of sense. That's why they're called fat trees, right? This is actually an example of a fat tree from it's a cluster called Stampede. It was, I think it's been decommissioned by now, but it was at the Texas Advanced Computing Center, which is in Austin at the University of Texas, very famous computing center. Also happens to be where the author of the textbook works. So that's why he's able to get all these cool pictures. But this is actually a fat tree implementation in real life that was used on an actual high-performance computing system. Not only that, I think I have some specs about that. Yeah, it was, so it debuted in 2013, which was a bit ago, right? But when this cluster first came online in 2013, it was the 7th fastest computer in the world. So an example of this topology being, and far from the only one that uses this kind of topology. Fat trees are a very, very, very common topology used in high-performance computing systems. What's the bisection width of this guy? Hope you saw that one coming by now. Where am I going to chop? Now be careful, because these switches are actually not part of our 2 halves, right? It's just these leaf nodes that are part of our 2 halves. So I don't care how many switches are on the left half and on the, I kind of gave it away. I don't care how many switches are on either half. I just care about how many processors are on either half. So clearly I think then just chopping either those four or those four would satisfy the true bisection. But again, trying to generalize that, where n is a power of 2, because again, this is a binary tree, so I'm always going to have a power of 2 number of leaf nodes at the bottom. In this case, I have 8 nodes with 4 being the bisection width, exactly half, and that turns out to be the general case as well. For n nodes, where n is a power of 2, the bisection width is going to be n over 2, half and half. And then the diameter, well, we can just use our good old binary search tree, or binary tree rules here. It's going to be 2 log n for the diameter, which is equivalent to the number of levels that we expect. Well, log n being the number of levels that we expect, we have to travel up and then back down. So that's where the 2 comes from in that particular case. Again, the reason why this is so common, having that scalable bisection width by number of nodes, as well as that logarithmic diameter, makes it a great candidate for high performance usage. All right, I think we already covered that. Bandwidth and latency. So all connections have some form of latency. There are lots of things that affect the latency. When you send a message, before the actual message gets transmitted, there's a whole handshake process that has to happen first so that the destination is prepared, is ready, right? The message just doesn't show up on the door and be like, surprise! They have to make sure there's space allocated to receive that message. So there has to be a buffer allocated to receive the message, and all that's part of the handshake process. That affects latency. That takes time. The message often, maybe less often in high-performance computing contexts, but, well, I don't know if that's true. It has to be encoded and decoded, typically, so on the sending and the receiving side. So that takes time, right? And then, of course, perhaps the biggest factor is just the physical amount of time that it takes for the light signals or whatever to travel down the wire. It's going to affect the latency. So we try to characterize this using the following formula. If you look at the textbook, they will expand this formula out a couple more forms, but I think this simple form is far more than adequate to express communication for our purposes. The alpha in this particular case represents the latency, where that latency I would expect to be actually roughly equal across, it depends somewhat on the topology, but the diameter is always going to be somewhat of an upper bound on that latency based on the number of hops affecting the travel time. The handshake and the encoding, decoding, those are going to be roughly constant, so less of a factor than the actual physical distance between the two. And then the beta here represents the time per byte, so how long it takes to transmit 1 byte across the wire, times n being used in this case, not for the number of nodes, but for the number of bytes in the message that we're trying to send. So a lot of models will use, maybe not this exact equation, but some augmented form of this equation, like the model that Austin was just talking about earlier today. I would not be surprised if they were modeling message speeds, probably using a little bit more complicated form of the equation than what's shown here, but something along those lines. I wouldn't be surprised to see that there at all. All right, we're going to take how much time I got? Oh, perfect. We're going to take a little bit of a detour. I'm going to talk about InfiniBand for like super briefly. Before I switch gears and talk about a different topic, I just want to pause, see if anybody has any questions about what I've covered so far. If not, we're going to talk about InfiniBand for just the briefest of moments, and then I want to show you an actual topology on an actual high-performance computer system to wrap up the day today. So let's talk about InfiniBand. And why do I want to talk about InfiniBand? Actually, this chart right here shows why I want to talk to you about InfiniBand. It is the most common type of interconnect used on the top 500. So this I'm going to be talking about stuff from InfiniBand that comes from the white paper that was released all the way back in 2003. I know that seems old, but still relevant today. It talks about the specs of InfiniBand. Mellanox Technologies, one of the big names in manufacturing InfiniBand equipment, although they got bought out. Anybody want to guess by who? It's a big name. You definitely heard of them. Jensen Huang at NVIDIA decided he wanted to buy out InfiniBand, so he did. They're owned by NVIDIA now, and NVIDIA makes all the InfiniBand stuff now. There used to be multiple vendors to manufacture and distribute InfiniBand products. Not anymore. It's NVIDIA, basically, that owns all that stuff. So anyhow, this is a graph from the top 500 page that shows what people are using. So InfiniBand is using over half, and then this other big chunk maybe is less surprising. It's Ethernet. Traditional Ethernet, like you would find, probably looked on the back of some of the computers in some of these labs. But why? Why are people using why are they not using Ethernet? Ethernet's been around for a long time. It is everywhere, right? Very well known. Lots of people know how to use it. So why? Why are we not just using this readily available, accessible, theoretically cheaper than this stuff, InfiniBand, which typically is only really used, I don't want to say only, but certainly is mostly used in the high-performance computing space. You're not going to run into InfiniBand on an everyday basis if you're just working with the regular kinds of network switches that you might find and routers that you might find in a typical user-facing network. So let's talk about why. This graph right here, I think, shows a lot of the reason why, not all of the reasons why InfiniBand is popular with high-performance computing. On the right is a typical breakdown of the transportation protocols that you would find in a typical network, the TCP/IP stack, basically. So the link layer and the physical layer of the stack are implemented in hardware, but then the transport and network layer are done by the OS, by the kernel, right? And then the user space, the application, is up there at the top. And then even on the routers, right, the link and physical layer are in hardware, but then the packet relay is often done in software. It's not maybe a full-fledged OS on the router, it's just the firmware, right? But still done on the software side, not the hardware side. On an InfiniBand node, you'll notice that there is no yellow. So we're cutting software out as much as we possibly can. Obviously, our user space application is still code, right? Our programmers are writing code that's going to run on top of all this stuff. But all of the transportation stuff, all the stuff that's required for transmitting messages from point A to point B is handled in hardware. All of it. And if you can do something in hardware, it's going to be faster than software. That's just been a general fact as long as I've been studying computing. So they are really trying to leverage that fact, that hardware typically faster than software at the cost of, well, they had to design all those circuits, they had to design all that hardware, and that's also why they get to charge you the big bucks when you want to buy InfiniBand and use it on your machine. So it's a switch, they call it a switched fabric, which really just means that lends itself really well to the kinds of switching topologies that we talked about. Fat trees, butterfly networks all work great with InfiniBand because they want to sell you their switches and they want to sell you all the other hardware that comes with their switches. That's what drives a big part of the InfiniBand's model. But there are some other advantages too. So increased bandwidth. For a long time, long time, InfiniBand classically had higher bandwidth across a line than the comparable Ethernet line would have. They were the first to get to 10 gigabit before Ethernet did. These days, that is actually less true than it used to be. Ethernet is caught up, and Ethernet is actually kind of tried to diversify and maybe borrow some of the tricks that InfiniBand used to try and catch up and deliver that increased bandwidth. So if you were talking to an InfiniBand salesperson, they would still say that, but in reality, not 10 years ago, yeah, not an unreasonable thing to say. These days, maybe less true than it absolutely used to be. Part of the way that it used to, part of the way that it got that increased bandwidth is that for a single connection, there's not just one line in there, but there's typically four 4 parallel lines for both sending and receiving in one connection, as opposed to Ethernet, which is you just got the one pipe and everybody's using that one pipe. And InfiniBand also provides other configurations where if you want to pay for it, you can actually have up to, I think, 12 in the same line, parallel going back and forth. So 4, I think, is by far the most common. And so their most recent, I have it here in my notes, the most recent architecture that they put out is called XDR, Extended Data Rate. They're getting 8 gigabits per second across a single link. That's with 4 parallel 200 gigabit lanes in both directions. Is how they achieve that 800 gigabit number. But as I said, that's comparable to what a lot of the higher end Ethernet stuff can do these days as well. They also actually get some of this increased bandwidth using something that Drew mentioned in his presentation earlier today, RDMA, which stands for Remote Direct Memory Access. So the whole idea behind Remote Direct Memory Access is if I'm a processor and I want to get a value from this other processor's memory, right? It's over here, but I want it. So I'm going to send a request to get that value. That request has to get processed on the software side. In a lot of cases, but remote direct memory access says, well, skip the software. I want to make it so that we can leave the OS out of it, we can leave the application code out of it. I can just directly access that memory location and then turn around and leave and go right back without having to bring any software into it at all. So that remote direct memory access really helps speed up not just the bandwidth, but also the latency. It's one of the big claim to fames of InfiniBand that a lot of other technologies have also latched onto. There's fewer protocols, so we're not dealing with TCP. InfiniBand doesn't do MAC addresses. InfiniBand doesn't do IP addresses. They have a single address for every component on the network that they call an LID, and I honestly can't remember what the L stands for, but that's it. There's no translation between IP address and MAC address. There's no having to look up, an IP address in the table, translate that to a MAC address. They just have that single ID number that's used for all routing within the network. And they also have increased reliability. So in a traditional TCP/IP implementation, it's possible for packets to get lost, right? Probably happens quite frequently when you're browsing the internet and things like that. And so think about what that means. That means that once it's realized that that packet is lost and never made it to the destination, it has to get resent. That's a big chunk of time to be spent now resending something when if it had just gone through the first time, would have saved us a bunch of time and effort. So they use a credit-based system that basically says on one side of the link it says, hey, I have this much buffer space, right? So you can send me this much stuff, but if you send me more than that much stuff, I'm going to be full up. So you're not allowed to send me any more stuff than I have buffer room for. So before a message gets sent, before a packet gets put on the wire, the sender has to make sure it has enough credits left to send it, make sure essentially that there's enough buffer space for that packet to be received, therefore guaranteeing that no packet ever gets dropped. It is actually a lossless system. InfiniBand is. It does not drop packets. It simply will not send the packet if it cannot guarantee that that packet is going to get received. Once packets reach their destination, they get those credits back, right? That allows them to continue sending more and more packets. But Ethernet has actually also implemented their own credit-based transmission system. So some Ethernet implementations are also lossless now, which is interesting. And part of the reason why you still see Ethernet hanging on, although to kind of wrap this all up and put a bow on it, a lot of people say that the biggest reason InfiniBand has a stranglehold on the high-performance market today is simply because it used to be better 10, 15 years ago, and people are just used to it now, and they don't want to switch. They don't want to do something new. So humans, right, have more to do with which, of course, that makes a lot of sense. Tradition holds a lot of weight with these kinds of things. People use what they know. InfiniBand got enough of a foothold when they were better than Ethernet, when they were doing things better than Ethernet, that even after the Ethernet started trying to play catch-up, there's still a big user base for InfiniBand. So doesn't seem like it's going to go away anytime soon, although it would be interesting to look at what this chart looked like. This is the most recent chart from November. The new top 500 is actually being announced at a conference in Germany. It might be today, because Germany is 7 hours ahead of us, but technically Tuesday. So whenever Tuesday is in Germany, they're going to be announcing the new top 500 list, which we will definitely talk about at some point. I'm looking forward to seeing it and seeing what changes there are. But let's wrap up today by talking about a very specific example. I think I have just enough time to do this. I might have to go a little bit quickly. Let's talk about the Tofu interconnect, which is a very, very clever name. It's a custom interconnect that's used by the Fugaku supercomputer, which we've already talked about in this class, I think, a couple of times now. It used to be the #1 computer in the world around 2020. It's currently number 7. It's got 7 million cores in it. It actually was used by, there's 3 different versions of this, so they've iterated over time, these improvements. The original Tofu interconnect was on the K computer, which is a former world #1 back around 2013, I want to say, is when it was the #1. And so developed by the Fujitsu company in Japan. They're like the center of HPC computing in Japan, consistently competing for the top spot on the top 500 list. And a large part of that credit goes to this fancy interconnect, this fancy networking system that they are using. So I want to spend a little bit of time talking to you actually about the first version of the Tofu interconnect, because it's not very easy to understand the modern version without first thinking about the first version and then talk about how they've improved it a bit since then. It uses a 6-dimensional network. So we're up to 6D, although it's more of a torus. Actually, the Tofu stands for, it's a clever name because Japan, they eat a lot of tofu. I eat a lot of tofu. I like tofu as well, but torus fusion is what it's short for. So they found a way to turn that into a clever name. It is a torus. It is, in fact, a torus. You can see that very clearly. I know this is a blurry image, but you can see that very clearly by these wraparounds here, that it is very much a torus. But the difference between a traditional torus and why they call it a torus fusion is that each one of these is not a single node, but then it's one of these little squares. Well, it's not a square. It's like a little cube, right? So within each one of these, we actually have another whole layer here. So there's 3 dimensions on this cube. See them labeled as X, Y, and Z, and then 3 more dimensions within each of these individual points on this grid to give it a total of 6 dimensions. And you can see these dimensions labeled as A, B being the between inner and outer, and then C being the other dimension there. So for a total of 6 dimensions. So incredibly complex. This is a custom design, right? This is not a design that's being replicated in many different systems. This is a very much custom design. I'm sure Fujitsu owns all kinds of patents. I don't know how patents work in Japan now that I think about it, but I'm sure they have all kinds of control over this. And it's really only used in this family of supercomputers. But as you can tell by the performance and how they do on the top 500, clearly they're doing something right. So how does it work? Well, it's a custom interconnect, so they designed a custom chip. This is actually an interconnect chip just to manage the messaging and the networking aspect. I'm going to have to go through this part real quick because I know I've only got about 10 minutes left. I think it's also safe to say, since we're talking about the exam, right? If you're thinking about what to study on this particular set of slides, the first part, right? I was talking about math today. We just did a whole bunch of, 2 to the n, log n. Like there's some good math that I could probably ask you on the exam. If you're studying for the exam, the first chunk that I talked about before the InfiniBand stuff, much more likely to be the content you're going to see on the exam than what I'm talking about right now. I might slip a question about the Tofu interconnect on there, but I'm much more worried about the general kinds of stuff that we're talking about. This is just meant to be a real-life case study. So I I could talk about all of these things in a lot more detail, but I don't have the time to do it, so I'm just going to kind of give you the high parts, the highlights. The host bus interface is used to connect the actual chips, the actual processor chips. There's actually 4 connections there, so each node in the Fugaku computer, or actually this is for the K computer, the first version, not the most recent version, had 4 chips in a single server case, essentially. And then these are the actual communication links, of which, again, there are 4. So they can send 4 messages at a time going in any direction that you want. So that's kind of what gives it a lot of its flexibility. There's a PCI Express up there to talk to other kinds of hardware and stuff. And then down here is the routing. So this is all, TNR stands for the Tofu Network Router. This is all baked onto one chip. Oh, and the TBI is the barrier interface, which is used for collective communications, which is a common kind of communication type. We'll talk about that a lot more, actually, when we get to OpenMP and MPI after the first exam. So moving right along here, we take a look at the router. I think the interesting thing to see here, this guy right up here, this yellow box, looks a lot like a diagram that I showed you a little bit earlier today. That's a crossbar. That's a crossbar switch. So there's an example of a crossbar being actually used in practice. You can see how it connects to the network interfaces. So there's both ins and outs. And then these down here, these link control modules, this is a transfer buffer. So if I want to send a message out, this is what I use. This is the buffer I use to send a message. These are receive buffers. So I have buffers for receiving messages over here. And then these DLLP buffers down here, these are for control messages. So just not for actual data, but for control messages to reprogram routers or do things like that. If I want to change numbering scheme of my nodes or shrink or expand, that's kind of what those messages can be used for to help configure the system. The Tofu network interface has a lot of parts, and I promise you I have all of these parts in my notes, but I'm not going to spend time going into detail because I don't have time to go through all of them in detail. I'll just kind of try and break it down to you simply. The stuff on the right-hand side is for transferring messages out. So all of these components here are used for transferring messages out. Everything on the left is for receiving messages, transferring messages in from a sender. And then the barrier interface, this is, again, another example of remote direct memory access. So this is specifically used only for collective operations, which is when we have one message that we want to be transmitted to many different recipients, or the opposite. I have one message that I want to be sent from many different recipients to one single destination. Those are collective messages. We'll go through that actually in a lot more detail, as I mentioned, but in order to really save time on those, you can see that traditionally we would go through the operating system and have to access memory and everything like that. They've set up their networks such that they can plant the data for these collective communications right down here in the interconnect itself, bypassing the OS, bypassing the access to main memory, and greatly improving time. That is remote direct memory access in action. Not the same way that InfiniBand implements it, but still remote direct memory access nonetheless. So that was actually all introduced in the first form of the Tofu Interconnect. They're actually up to the 3rd iteration of Tofu Interconnect. So the first one was just called the Tofu Interconnect. The second one was called Tofu 2. And then for the 3rd one, for some reason, they switched to letters and skipped to the 4th one. So they called it Tofu D. I don't know. That's what they called it. It's the 3rd one, though. The biggest difference between Tofu 1 and Tofu 2 is that they took the chip that I showed you in the previous slide, and they integrated it directly into the CPU. They're using Spark processors on their machine, so they actually have, I don't think I included a diagram of it on this slide, maybe I should have, but they actually took all of this stuff they were able to shrink it down and get rid of the host bus interface entirely because they just took all of this silicon, all of these transistors, and embedded them directly onto the CPU, directly onto a Spark chip. Again, custom design, right? Custom designed Spark chip. Lots of money, lots of time. Fabricating chips is not a simple thing to do. So clearly they were invested in doing it this way. But that was the big change between Tofu 1 and Tofu 2. And then with each successive iteration, what they've, with the biggest difference then between Tofu Interconnect D and Tofu 2 is they've increased the number of channels. It used to be only 4 channels. They beefed it up to 6. Beefed it up to 6 channels with which to send messages. And interestingly, with each iteration, the bandwidth of the channels has actually decreased. Right? So they've actually shrunk the size of the message passing channels, but the performance has improved. Well, from 1 to 2 it improved simply because it was co-located on the chip, which just makes it so much faster than having that extra step between the two. But then here they increased by adding those extra channels. So they decreased the bandwidth of the channels, but ultimately net positive because there are now 2 additional channels as opposed to 4. That's how they got a big improvement bonus. That's not the only differences. Again, I'm just kind of giving you the highlights here. You can take a look. I've linked. I've actually put both of these papers on Canvas if you're interested in reading more. Here are just some basic numbers showing the comparisons, but this is actually, I think, the most illustrative chart. The thing I like about this chart, between Tofu 1, Tofu 2, and Tofu D, you can see that entire sections of it just disappear, right? So these 2 sections, you can see between Tofu 1 and Tofu 2 just disappeared simply because they didn't need them anymore. It was no longer 2 separate pieces of hardware talking to each other. It's now just one piece of hardware. So we don't even need that part anymore. We don't need the stuff with the host bus anymore. That's instant savings. You can see that the packet transfer actually increased between Tofu 1 and Tofu 2, but then they figured out how to bring it back down again for Tofu D. I don't have a whole bunch of time to go into all the specifics. I would love to, but we're out of time. And I'm tired, and I bet you all are tired too. So I'm going to go ahead and call it here. Thank you all once again for paying attention and putting up with me asking you what the bisection width is about a dozen times today. I will see you on Wednesday for another round of student presentations. I'm really looking forward to it. Thanks.